Greetings, everyone. Learning as a hobby here. I wanted to finally go ahead and do my summary for section 5.5 in Spivak's, sorry, not Spivak, Terrence Tao's Analysis 1 book. So let's get through that. There's only this section and the next section left for chapter 5, and then we'll be back to Spivak. So I think I got Spivak on my mind here. Let me bring up my notes or my summary for section 5.5. We'll go through it. Okay, so in this section, we're going to show that the number set, the real numbers that we constructed using Cauchy sequences, has the property that we want, which is the least upper bound property. The fact that the real numbers have the least upper bound property is what makes them better for our purposes than the rational numbers, for example. So let's go through it. Before we define what a least upper bound is, we need to know what an upper bound is. So that's definition 5.5.1. All right, so here tau defines upper bound. Let E be a subset of the real numbers, and let M be a real number. We say that M is an upper bound for E if and only if we have X less than or equal to M for all X in E. So hopefully that's a pretty intuitive definition. Okay, he gives us some examples here. So example 5.5.2, let's say that we have the subset of the real numbers E, which is defined to be the set of all real numbers X, such that X is between 0 and 1. Then any number greater than or equal to 1 is an upper bound for E because it satisfies the definition, right? Any number in that set is less than or equal to 1. All right, he gives another example here of the positive real numbers. So let R with the superscript plus stand for the set of all real numbers X that are greater than 0. So the set of positive real numbers. All right, then he says this as a statement in the example, but he asks again the reader to prove, or he asks them why. So whenever he says that, I like to prove it. So that's why I have it written as a proposition here with no number after it. All right, so the statement is that set, the positive real numbers, has no upper bounds. He has a note here also on the side. He says the extended real numbers, which he denotes as R with a superscript of star, are bounded, and we'll look at the extended real numbers in section 6.2. So we're not going to look at that in this section, but a couple chapters from now. All right, so here's my proof. Again, like I said, he asks the reader to supply this, so here's my proof of that. So assume for the sake of contradiction that M is a real number, is an upper bound for R plus, then 1 is less than or equal to M, which implies, because 1 is an element of that set, right? Implies M is greater than 0, and exercise 5.4.3 implies that there is a natural number capital N such that capital N less than or equal to M less than capital N plus 1. Since 0 is less than M is less than capital N plus 1, that implies that 0 is less than capital N plus 1. This contradicts that N plus 1 is less than or equal to M by hypothesis. Therefore, that means that that's our contradiction, right? So that means that R plus has no upper bounds. Okay, he gives another example here. So every number M is an upper bound for the empty set. And this is a vacuously true statement. Why? Because there are no elements of the empty set. Right, so finally, here's our definition of what we mean by a least upper bound. Let E be a subset of the real numbers and M be a real number. We say that M is a least upper bound for E, if and only if. So there's two parts. A, M has to, first of all, be an upper bound for E. And then part B, any other upper bound, M prime, let's say, for E must be larger than or equal to M. Right, so it's the smallest of the set of upper bounds for the set. Okay, another example just to illustrate the concept. Let E be the same set that we had defined up above, the set of all real numbers such that X is between 0 and 1. Then 1 is not only an upper bound for that set, it's the least upper bound. All right, and he has another example here where he asks, he makes a statement and then asks the reader why. So again, I'm just proving that here. So this is example 557. The statement is the empty set has no least upper bound. And here's my proof. All right, so assume again for the sake of contradiction that M is a least upper bound for the empty set. Let epsilon be any number greater than 0, then M minus epsilon is less than M. Then for any x in the empty set, x is less than or equal to M minus epsilon, which is less than M, which that follows just trivially, right? Because there are no elements of the empty set, which contradicts that M was the least upper bound. Therefore, there are no least upper bounds. All right, next we get a proposition which states that least upper bounds are unique. This is proposition 558. Let E be a subset of the real numbers, then E can have at most one least upper bound. All right, so here's the proof. Let E be a subset of the real numbers and assume E has least upper bounds M and M prime. Then M equals M prime, M is greater than M prime, or M is less than M prime by trichotomy. But the last two cases can occur because M and M prime are least upper bounds. So one can't be greater than the other and one can't be less than the other, in other words. So that's our sorry, not by contradiction. That means that the only thing that's left is that M equals M prime, and therefore that's the conclusion. All right, then he has a theorem here, 5.5.9, which I'm not going to prove here, but let me read it out first. This is about existence of least upper bounds. Let E be a non-empty subset of the real numbers. If E has an upper bound, then it must have exactly one least upper bound. Now, Tao does prove this in the book, but I'm going to leave it to the video when I get to the exercise set, and that's because what happens in Tao's proof is he relies on a bunch of lemmas that he actually asks the reader to prove in the exercise set. So that's exercise 552, 553, 554. So I think it'll be just a better, the proof will flow conceptually better if I prove those lemmas first and then just I'll do the proof in the video in the exercise set just for readability reasons. So I'm going to hold off on actually doing the proof for this until the exercise set video, which should be the next video that I put out. All right, so we'll hold off on that one for now. All right, definition 5510. This is the definition of supremum of a set. Let E be a subset of the real numbers. If E is non-empty and has some upper bound, we define sup E, which stands for the supremum of the set E, to be the least upper bound of E. And we know that this is well defined by theorem 559, the one that we just talked about but didn't prove. We introduced two additional symbols, plus infinity and minus infinity. If E is non-empty and has no upper bound, we set supremum E to be equal to plus infinity, and if E is empty, we set sup E to be negative infinity. We refer to sup E as the supremum of E and also denote it by sup E without the parentheses, so either way. All right, Tao has a remark here, 5511. At present, plus infinity and minus infinity are just meaningless symbols because we haven't talked about how they interact. How do you add them? How do you do with the algebraic operation, arithmetic operations on them, right? In section 6.2, we add plus minus infinity to the reals to form the extended real number system, but the system is not as convenient to work with because many of the laws of algebra actually break down. For example, defining plus infinity plus minus infinity is problematic. So in 6.2, though, we'll extend our set of real numbers to the extended real numbers, which will be useful for certain things, not as useful for other things. But anyway, that's Tao's remark. 5511. All right, we have another proposition here, 5512. There exists a positive real number x such that x squared equals 2. So here's where the real numbers start to shine. There's a square root of 2 that exists in the real numbers, right? Okay, here's the proof, which is a little bit involved, but we'll take it a little bit of time. So let E be the set of real numbers y such that y is greater than or equal to 0 and y squared is less than 2. Right, then E is bounded above by 2, for example, since if A is greater than or equal to 2, then A squared is greater than or equal to 4, which is greater than 2, which implies that A is not an element of E. Also, E is not empty since 1 is greater than 0, and 1 squared is 1, which is less than 2. So 1 is, in other words, 1 is an element of E, so E is non-empty. Right? Then E has a least upper bound. We'll call it sup E, so X equals sup E. Furthermore, X is greater than or equal to 1 and less than or equal to 2, since 1 is an element of E and 2 is an upper bound for E. So in other words, since 1 is an element of the set E, we know that the supremum has to be greater than or equal to that number by definition of supremum, and it has to be less than or equal to 2 because the supremum is the least upper bound, and we know that 2 is an upper bound for the set E. All right. Therefore, by the fact that X is between 1 and 2 implies that X has to be greater than 0, so it's positive. Right. So we've shown that there exists a positive real number X that is at least the supremum of that set. All right, next we have to show that X squared is equal to 2. So we're going to do this by contradiction. So we'll first assume that X squared is less than 2, all right? So we'll do that for the sake of contradiction. Then there's some epsilon such that epsilon is greater than 0 and less than 1, and X squared plus 5 epsilon is less than 2. Right, we can do that because X squared is less than 2, right? We're by assumption. Right, then X plus epsilon squared is equal to X squared plus 2X epsilon plus epsilon squared, which is less than X squared plus 4 epsilon plus epsilon, because 2X epsilon is less than 4 epsilon, right? X is less than 2, so 2 times 2X, 2 times X is less than 2 times 2, which is 4, and epsilon squared is less than epsilon because epsilon is a number between 0 and 1. All right, and you could just simplify that. That equals X squared plus 5 epsilon, which is less than 2. Right, we chose epsilon to be a number that has that property. All right, that implies that X plus epsilon is an element of E, which contradicts that X is the supremum of the set E. Right, so that leads to a contradiction. Maybe X squared is greater than 2, so let's try that. Right, then there's some epsilon such that, again, epsilon is between 0 and 1, and X squared minus 4 epsilon is greater than 2. We can do that because X squared is greater than 2 by our assumption. All right, then if we look at X minus epsilon squared, that equals X squared minus 2X epsilon plus epsilon squared. That's greater than X squared minus 2X epsilon because epsilon squared is a positive number, right? And that's greater than or equal to X squared minus 4 epsilon because we know that X is greater than or equal less than or equal to 2. So negative, if you negate, you get negative X is greater than or equal to 2, which means that negative 2X epsilon is greater than or equal to negative 4 epsilon. So that's where that comes from. And we know that that's greater than 2 because we chose epsilon to have that property. This implies that X minus epsilon is an upper bound for E, since if X minus epsilon is less than or equal to 0 for some y in epsilon in E, then X minus epsilon squared less than equal Y squared less than or equal to 2, which contradicts that X minus epsilon squared is greater than 2. Then X minus epsilon is an upper bound for E, which contradicts that X is the supremum of E, right? Therefore, the only thing that's left by trichotomy is that X squared has to be equal to 2. Therefore, that's the number that squares to give you 2. All right, so that proves that there is a square root of 2 in the real numbers. All right, now that's not the only, it's just one number, but one thing that the least upper bound property tells us about the real numbers is that there are no gaps in the real numbers, whereas there are gaps in the rationals. Okay, then there's just a couple of remarks that Tao has at the end of this section. The above proposition demonstrates that some real numbers are not rational. Furthermore, it shows that the rationals do not possess the least upper bound property, since if it did, we'd be able to prove that square root 2 was rational, which by proposition 4.4.4 is not possible. All right, then he has another remark right after that. In chapter 6, we will use the least upper bound property to develop the theory of limits. But like I said, that's a couple chapters from now. So we're not going to do that in this section. Remark 5.5.15, which is the last remark in the section. We can talk about lower bounds and greatest lower bounds, which we call the infimum. If E is a subset of the real numbers that is bounded below, E has a greatest lower bound denoted by inf E. A precise relationship between sup E and inf E is given by exercise 5.5.1. So we'll see that in the exercise set. And then also he says C, also section 6.2. And that's the end of my summary for this section. It wasn't that long. There's a few problems in the exercise set. So let me just stop my screen share. So in the next video, we'll do the exercise set. Like I said, there's exercise 5.5.2.3.4 are lemmas that you need to prove that proposition about the existence of least upper bounds. So we'll do the exercise set questions, and then after that, at the end of the video, I'll do the proof for that lemma, which should flow a little bit more easier because I don't have to go prove these lemmas first or whatever. So we'll have them already proved, and we could just say by this thing, by this thing, by this thing. So I think it'll just make the proof flow a little bit easier and make more conceptual sense when I explain it. Okay, so that's the end of this video. Like I said, next video will be on the exercise set. Hopefully I'll be able to get that out in the next couple of days. Give me a like and subscribe, guys, if you enjoy this content and want to see more, and let me know what you think down below, and I'll see you guys in the next video. Keep learning, everyone.